We are Mariana Luna and Ricardo del Rio, mentored by Professor Alejandro Rivero and Luana del Ruiz from the Electrical and Systems Engineering Department at Penn, and this talk is about gated graph recurrent neural networks.
In machine learning, there are many applications that involve learning from real-time data, like natural language processing. In supervised learning, the objective is to map sequential input data xt to some target output yt. We assume that the data points in xt are related through some dependency relationship f, that is, xt plus 1 is obtained by applying f to past elements. This set of dependence relationship can be modeled by a hidden Markov model with state variable ht that stores relevant past time information, and we can now model xt plus 1 as only depending on the input at the previous time step xt and on the state variable ht through some function g.
Recurrent neural networks approximate the hidden state according to this expression, where A is a linear transformation mapping x of t to the state at time h of t. B is a linear transformation mapping the previous state h of t minus 1 to the current state h of t, and sigma is a nonlinear function, usually the hyperbolic tangent. The representation estimate y hat of t is then calculated from the state h of t as rho c of h of t, where c is a linear transformation mapping the state to the output and rho is an arbitrary nonlinearity.
Many problems are very modeled as graph processes. An example of graph process is, for instance, the spread of an infectious disease in a commuter traffic network connecting states counties. In this type of problem, the graph is captured by the graph shape of a radial matrix S. The ijth element of S gives a measure of a proximity between nodes I and j of the graph, in the case of a traffic network, the counties. The data is captured by the vector xt, whose ith element corresponds to the value of the data at the ith node. In the example where the data is the number of cases of an infectious disease, xi will be the number of cases at county I.
Graph recurrent neural networks are architectures made to exploit both the sequential and the graph structure of the data. To take the graph structure into account, we parameterize the linear transforms A and B by the graph through the graph operator S.
We choose to use graph convolutions. The benefit of this parameterization is that because it is a polynomial in the matrix S, the number of parameters does not depend on the number of nodes of the graph, which can be very large in certain applications. These convolutions are also permutation invariant, meaning that the labeling of the nodes does not affect its results.
The basic GRNN or any RNN is bad at working with strongly or weakly correlated sequences that have long-term dependencies. They might get assigned exponentially larger or smaller weights, causing the gradients to explode or vanish. Normally, this is solved by adding input and forget gates, represented by the scalars alpha t and beta t respectively. Both of these gates take values between 0 and 1. Alpha of t controls the importance of x of t at time t. Beta t controls how much weight we give to the previous state h of t minus 1. This mechanism that we'll call time gating prevents the gradients from exploding or vanishing, therefore improving the learning process.
Given that we're using a graph as well as a sequence, there can be spatial dependencies that can become problematic. So we can implement a more sophisticated gating strategy that takes the graph structure into account to address long-range spatial dependencies. In node gating, this is done by assigning one input gate and one forget gate per node of the graph. Two GRNNs calculate the input gate and the forget gate states. Then, these states are fed to the GNNs, which output single feature graph signals, followed by the sigma to make sure that the gates take values between 0 and 1.
In the following, we present a series of numerical experiments showcasing the advantages of GRNNs in gating. The first experiment is a 5-step noisy graph diffusion, where we simulate the noisy graph diffusion process given by x of t equals s of x t minus 1 plus w of t, where w is a Gaussian noise. The problem we are trying to solve here is to predict x5, x6, x7, and so on from x0, x1, x2, etc. We train a GRNN, a GNN, and an RNN, all with the same number of parameters, to solve this task. These are the results we obtained. The table on the left shows the relative root mean square error achieved by each architecture. Note that the GRNN does better than the GNN and the RNN. This is expected as the GRNN leverages both the time and the graph structure of the data in the learning process, unlike the GNN, which only takes the graph topology into account, and the RNN, which only takes the sequential structure into account.
The main experiment consisted of predicting fluke cases on a transportation network based on a commuter traffic network connecting the 62 counties in New York and on the fluke cases registered in 2010. The sequential data were the number of accumulated cases in each county for every 4 weeks of the last 8 weeks of 2010 and the first 4 of 2011, which we used to predict the number of cases in the weeks 8 to 20 of 2011. Given that we were relying only on one dataset, that is, one snapshot of a history of flu cases in New York, we decided to split the counties, the nodes of the graph, between the training, validation, and test nodes. That is, we were going to train the neural networks on the first nodes and test it on the last ones. With the first set of hyperparameters on the neural network, we could only reach around 89% of error. After many iterations and adjustment of the learning rate, the architecture of the network, and the number of training, validation, and test nodes, we achieved around 59% of error, noting that the network was indeed learning. We also implemented node, age, and time-gated GRNNs, but this output an error of around 90% in average, meaning that the dataset that we had did not have long time or range dependencies, making a normal, non-gated GRNN more suited for the job. In order to bring that error down, we will have to increase the number of datasets. That is, having more years of fluid data and traffic networks and combining them to have more training data. That is left as future lines of research.
In these experiments, we use simulated data in a similar setting of that of five-step prediction to compare the performance of different gating techniques. First, we simulated a noisy autoregressive process with a parameter given by x of t equals ax of t minus 1 plus w of t. W is once again a Gaussian noise, and the objective is to predict x 10 steps ahead. We compare a GRNN and a time-gated GRNN for multiple values of a between 0 and 1. The plot shows that we can see that for a bigger alpha, a larger time dependency, we have a better performance by the gated version of the GRNN. When alpha equals 0.7, we have a decrease in the relative performance, but this might be due to outliers.
For not gating, we now consider a process like the one in the previous experiment, where now S, the graph shift operator, is exponentiated by the scalar a between 0 and 1. We predict the values of x 10 steps ahead. The architectures that we compare are a GRNN and a node-gated GRNN. The relative RMSE improvement of a node-gated GRNN over the GRNN is presented on the plot. We see that the performance has improved in most of the cases, given that the input of the gates are retaining or deleting information in exchanges across the graph. We can see that it only is worse when a equals 1, meaning that we don't see an improvement when s is not altered.
To conclude, we have introduced gated graph recurrent neural networks. GRNNs are tailored to problems involving graph processes. They are able to exploit the local graph structures present in this type of data through local graph convolutions. They also exploit the sequential nature of data through this state recurrence. We followed by introducing time, node, and edge gating mechanisms, which allow GRNNs to accurately encode long-term dependencies and long-range dependencies on the graph. We have observed performance of improvements of GRNNs over GNNs and RNNs in two experiments, a synthetic experiment of case-step prediction and a real-world experiment of fluke cases estimation.